Good morning. Today we are going to start with the second topic of application of derivatives, which is increasing and decreasing functions. Now let us first consider the mathematical definition of increasing and decreasing functions, and then we will elaborate upon each of them. Now it says that if y is a function of x such that x1 less than x2 implies that fx1 is less than fx2, it is called as strictly increasing function. x1 less than x2 implies that fx1 is less than or equal to fx2, it is called as increasing function. Likewise, if x1 less than x2 implies that fx1 is greater than fx2, it is called as strictly decreasing function, and fx1 is greater than or equal to fx2, it is called as decreasing function. Now what exactly do we mean when we write all this? Okay, now let's consider any function y equal to fx having a graph something like this. Okay, so as you move from left to right along the x-axis, so clearly if suppose x1 is here and x2 is here, you can see that this is fx1 and this is fx2. So as we move from left to right along the x-axis, that is when x2 is more than x1, we see that fx2 is more than fx1, and clearly the graph says that it is increasing. So such a function is called a strictly increasing function. Okay. Similarly, if we have a graph like this, that this is x1 and this is x2, as we move from left to right along the x-axis, this is fx1, this is fx2. As x increases, the value of fx decreases. Clearly fx2 is less than fx1. Such a function is called as strictly decreasing function. Whereas if we have a graph something like this, that this is x1, this is x2, this is origin, that is if we are moving from left to right along the x-axis, that is when x2 is more than x1, we have fx2 is equal to fx1, means the value of fx remains the same. So it is neither increasing nor decreasing at this point, or we say it's a constant at in this interval from x1 to x2. Okay, so now if it is this category, that is when x1 less than x2 implies fx1 is strictly less than fx2, it is called as a strictly increasing function. Same way this one is called as a strictly decreasing function. If it's a combination of both strictly increasing and constant function, that is x1 less than x2 implies that fx1 is less than or equal to fx2, we call it an increasing function. The word or the term strictly is removed from here. Same way, if it's a combination of strictly decreasing and a constant function, okay, so then it is called as a decreasing function. The term strictly is dropped from here, and the graph is somewhat like this. If you just see, it could be, you can have something like this and then this. In between there are points where the value of fx1 is equal to fx2. So this is a increasing function. Whereas if you have a graph something like this and in between there is a line parallel to the x-axis, such graph or such a function is called as a decreasing function. Okay, so the fifth definition we will write that if x1 is less than x2 implies and implied by fx1 equal to fx2, this is called as a constant function. Here this means strictly. Okay, now let's take up the questions which we can do, but first we will do one question by the basic, that is this concept, and then we will do a theorem which gives us a result using which we can check whether the given function is increasing or decreasing. Okay, so let's take up an example which says that fx is equal to 7x minus 3. We have to show that is increasing on real numbers. Okay, so what do we do? So let x1 be less than x2. It implies that 7x1 will be less than 7x2, which implies that if you subtract 3 from both sides, the inequality sign remains the same, and so we have 7x1 minus 3 is less than 7x2 minus 3, and which implies that fx1 is less than fx2, which implies that fx is increasing. Okay, now this is a very simple way of doing it, but not every question can be done this way. So we need to find a simpler and a direct method of proving, or some formula for finding whether it's an increasing or a decreasing function. Okay, now in order to find whether a function is increasing or decreasing at a point, let's say x0, if and only if we can find we can find an open interval AB such that x0 belongs to that interval and the function is increasing or decreasing respectively in that interval. So what we see is that to check the increasing or decreasing quality of a function at a point, we simply need to find an open interval containing that point such that the function shows increasing or decreasing property in that interval. Okay, now let's take up a theorem which says that let f be continuous on closed interval AB and differentiable on open interval AB. Then there are three conditions which are satisfied. First is that f is increasing in the closed interval AB if f dash x is greater than 0 for every x belonging to open interval AB. Second is f is decreasing in this given interval if f dash x is less than 0 for all x belonging to AB, and the third one is f is a constant function in the given interval AB if f dash x is equal to 0 for all x belonging to the open interval. So here these are the three conditions, this and this. Now in order to prove this theorem, we will have to make use of the mean value theorem which we did in the previous chapter. Okay, now as we can clearly see, both the conditions of the mean value theorem, means Lagrange's mean value theorem, are satisfied here. That is, the function is given to be continuous in the closed interval and differentiable in the open interval. So very obviously, since the conditions for mean value theorem are satisfied, so then there exists at least one point C belonging to the open interval such that f dash C is equal to f B minus f A over B minus A. Okay. Now here, so let's start. This is the mean value theorem. So let's use this to prove the given function. Okay. So now consider. So this is mean value theorem. Okay. Now consider the function y equal to fx, okay, which satisfies this, okay, and let x1 be less than x2, as is the condition which we do always, okay. So therefore by mean value theorem we have f dash C will be equal to fx2 minus fx1 upon x2 minus x1. This gives us fx2 minus fx1 is equal to f dash C into x2 minus x1. Okay. Now given that x1 is less than x2, it implies that x2 minus x1 is greater than 0. It implies that f dash C has the same sign as fx2 minus fx1. Okay. Now this gives us, now we know that the function fx is increasing when fx1 is less than fx2. That is fx2 minus fx1 is greater than 0, which implies that f dash C is greater than 0. Decreasing when fx1 is greater than fx2, that is fx2 minus fx1 is less than 0, it implies f dash C is less than 0. And constant when fx1 equal to fx2, that is fx2 minus fx1 equal to 0, which implies that f dash C equal to 0, hence proved. Okay. So let's do some questions on this. So we start with exercise 6.2. Question number 1 says fx equal to 3x plus 17. We have to check whether it is increasing or decreasing. First method of doing it is simply let x1 less than x2. It implies that 3x1 less than 3x2, which implies that 3x1 plus 17 is less than 3x2 plus 17, which implies that fx1 is less than fx2, which implies that fx is increasing for all real numbers. Okay. The other one, this kind of question can be done directly with this, but it can also be done by the theorem which we have done. So let's find, or f dash x equal to 3, which is always greater than 0, it implies that fx is increasing for all x belonging to real numbers. Okay. Now same way you can try the remaining questions till question number 5. or let's say till 4, but first I'll just take up question number 2 also, a similar one. Fx equal to e raised power 2x, it implies that f dash x equal to 2 e raised power 2x, which is always greater than 0 for all x belonging to R, and it implies that fx is increasing on R. Okay. So, try out the remaining questions and we will continue with next type of questions in the next video. Thank you.